Hi. First of all, thank you very much for letting me come and talk to you tonight. Um, I've known about Fermilab. I'll explain it to you more. I've known about it since before it was built. I had an older brother who taught me everything about astronomy and physics and science of all kinds, and he told me they're going to be building Fermilab and what it's going to do. And it got into my head that if our government is going to spend any money, this is the kind of thing they ought to be spending money on. Okay, and so it was 30 minutes from my home. I've been there many times. I knew some people who worked there, so I just wanted to tell you what I know about it. Okay, and I got a lot of stuff to tell you. I'm going to go kind of fast, but please stop me and what? I should do this better. Clip me. Yes, I do. See? Yes. I'll tell you a little bit about this in a little while. Anyway, I got several of them. So Fermilab, what is it? This is the big building that they have over there, their headquarters, but it's a particle physics laboratory. What does a particle physics laboratory do? It's where scientists study fundamental constituents of matter, subatomic particles, radiation, and the forces that govern them. And when they say fundamental, they mean, this is what they thought, they mean you break it down to these particles and you can't get any smaller than this. These are the fundamental particles. These are what the smallest possible particle that makes up everything. And that's what they thought that they were doing. And then they learned better later. Okay, so Fermi, well, let's see. And my thing didn't work here. Oh, it is, it's just slow. Believe it or not, that's part of the Fermilab presentation. Okay, it works slowly. Okay, so I already did this one. Okay, so I hit it. All right, so founded in 1967, named after Enrico Fermi. He was a theoretical physicist back in the 30s, 40s, Manhattan Project, etc. Largely funded by the Department of Energy. 38 countries plus the CERN laboratory in Switzerland, if you're familiar with another similar laboratory, all participate in what's going on at Fermilab. It's a very international organization, right? First director was Robert Wilson, Nobel laureate scientist from 67 to 78. In 1972, their accelerator, and I will explain to you what an accelerator is, okay? But their big deal was their accelerator achieved 200 billion electron volts, which was the biggest in the world at the time. Why do you want powerful accelerators? Because the accelerator smashes particles together to break them up into pieces so we can see what's inside them. You don't have to go to class. That's the whole class right there. That's what particle physics is all about, right? You want to see what's inside them. And they always brag whenever you go to a presentation there. And we got it built ahead of schedule and under budget. So that was always a nice thing to brag about. In 1980s, they upped it from 200 billion electron volts to 1 trillion electron volts. So they were, again, the biggest in the world. 1 TeV, so they call that big machine the Tevatron. Okay, and I'll show you what I can about that. Okay, I hit the button again. On this screen, well, anyway, if you look at my shirt, I don't know if can people see people online can see my shirt, right? Okay, you see the logo for Fermilab. So the last time I visited there, I went into the gift shop. They have a gift shop. This is like Vegas, okay? And so you see the logo on the bottom of the screen there and on my shirt. And I said to the lady in the gift shop, I wanted to buy a couple of shirts. And I said, so this looks like a lowercase f for Fermi, and they put 4 of them together for their logo. And she said, no, you're incorrect. That's not what it is. She said, the curved lines are the dipole magnets in the accelerator, and the 2 horizontal lines, wait a minute, I got that right? And the curved lines, I'm sorry, are the quadrupole magnets. She knew it better than me, okay? And the 2 horizontal lines are, all I have to think, and the thing appears in the correct place. This is wild. And the 2 horizontal lines are the dipole magnets, which are used in the accelerator. And I thought, I got put in my place. I'm Mr. Science guy, Okay, and the lady in the gift shop is giving me a engineering lecture, and I saluted her. She was fantastic. Anyway, so that's the logo for Fermilab. Okay, all right, and you saw this before. Ever since Fermilab was built in the 60s, they have it's a giant ring. You'll see that, a giant ring, 4 miles in circumference. So there's a whole big empty area in the middle of it. So they brought in a whole bunch of American bison. Some people call them buffalo, okay? And there's a herd of them. And when I looked up, they were always having new bison over there. They were getting babies every year. So they have this ongoing herd there. Why? To stay connected with the Illinois prairie, which is where they are. They're 45 minutes west of Chicago, okay? So they wanted to have that Illinois prairie presence in the buffalo. And there's to this day, after all those years, they have the buffalo roaming and you can go see them. Okay. Let's see, next screen says, okay, so this is a picture from way up high, and let's see, I have this. Okay, so here is the Tevatron. The first picture had that skyscraper you saw, that's their headquarters, their office. Here's the giant skyscraper over here, okay? Here is the Tevatron, the big ring, 4 miles in circumference. And I'll give you more details about it. These are the experiment areas, and I will show you what all that is. So 1 trillion electron volts. Leon Letterman was the director when it was built. And for 44 years, it was the most powerful one in the years. Most powerful one, I have to slow down. I'm always told to slow down. It was the most powerful one in the world for 44 years. It became the second most powerful when CERN was built in Switzerland 15 years ago or whatever that was, okay? 4 miles in circumference. And what does it do? It collides protons with antiprotons, as I alluded to before, to break them, to smash them up, to see what they're made out of. And they've had a lot of success doing that at Fermilab. So they made some discoveries. In 1977, the bottom, I'll try to explain some of this a little bit more later. The bottom quark, in 1995, the top quark. In 2000, the tau neutrino, which I'm sure you probably all went to that party when they discovered the tau neutrino, sure, right. And 2008, the bottom omega baryon, which is a particle that has 2 strange quarks and 1 bottom quark, in case you were wondering, okay? 2011, they were replaced by the Large Hadron Collider, that's CERN, okay, Switzerland, which has not 1 trillion electron volts, but 6.8 trillion electron volts. So it is, they really raised the bar, as the saying goes, okay? And so now, so what is Fermilab going to do, right? If you want to do the proton research, you go to CERN. So Fermilab is now doing neutrino science, and they are the premier place in the world for finding out about neutrinos, which are mysterious, okay? And the current guy who's running the show is Norbert Holtkamp, if I'm pronouncing that correctly. So this is what it looks like. Okay, I hit the button. So I mentioned quarks. Some of you, okay, who here has heard of Fermilab before tonight? Lots of you. Okay, fine. What about quarks? How many people have heard of? Okay, it made the papers, right? Quarks. Okay, so we've learned a lot about subatomic particles, the so-called fundamental particles. Okay, and so you pile them all up into a graph, and you come up with the standard model of elementary particles. So you've got these 6 quarks. You've got 6 leptons. I'll explain these a little bit more. And then some bosons and the Higgs particle. Higgs was discovered at CERN. You might have heard it. That was a big deal. So what the heck are quarks? There's top and bottom, charm and strange, up and down. The names are totally arbitrary. If you discover it, you get to name it. Okay, I guess. Like a comet, right? So a proton, we are familiar with them. There are some in this room, as a matter of fact. Several. I counted some. A proton is made of 3 quarks, an up, 2 ups, and a down. If you got 2 ups and a down, you got a proton, okay? A neutron, which is the same as a proton, or very similar to a proton, except it doesn't have a positive charge, it's neutral. It doesn't have an electric charge. It has 2 down quarks and 1 up. All right, so that's the difference between a proton and neutron, aside from their charge. So quarks are those so-called fundamental particles that you can't break any smaller, Okay, these are the kind of things that Fermilab was looking for, and they found lots of them. Okay. Oh, and how do they do it? I think I'm going to get to that, but they take protons over here and antiprotons, and because they're both charged particles, they can control them, smash them into each other, and that's how they break them up and discover things. Okay, we're going to talk about that. So I knew a guy, okay, and I got to go to inside Fermilab many times, okay, and it's like nothing else on the planet, right? So they have to, the accelerator, it comes in many stages to get the particles traveling fast enough. So it starts with stage 1 over here. This thing is called a Cockcroft-Walton accelerator. You can't tell in this picture. I stood right underneath it. It's about 35 feet tall. It's a giant electronic thing, okay, that takes protons and accelerates them. Okay, what does it do? It says here, makes negative ions, so it strips some of the electrons off of them, okay? And it accelerates them to the tremendous speed of 750,000 electron volts, which, as it says here, is 30 times your old power of your old TV tube. Who here is old enough to remember the old TVs? Some of us, okay? So there was an actual electron gun, an electron accelerator in the back of your old TV that shot electrons toward the screen, and that's what made the picture. That's Einstein gave us the theory for that, okay? And so that was a particle accelerator in the back of your TV. I never thought about it when I was a kid, but that was what it was. 750,000 electron volts. It just shoots them out this way into this stage 2 linear accelerator. What is it, 500 feet long, and accelerates them from 750,000 to 400 million electron volts. So, and how do they do this? When you have a charged particle, you can control it with magnets, and you can pull it with the magnets. To put a long story short, you pull them and you pump energy into these particles, and that's what accelerates them. So that's how all these accelerators work. So they get them up to 400 million electron volts and take all the electrons off. So all you got is protons now. We're getting close to what they need. It goes into stage 3. It's a ring. Here's the ring. This is a picture I took from the top of that big skyscraper looking down, okay? And that's the booster ring. There's 2 booster rings. This is one of them. Never mind. It's 20 feet underground. The protons travel around it 20,000 times, probably in less than a second, okay? And they accelerate them up to 8 billion electron volts. So faster, faster, faster. The faster they go, the more they can break them up to see what's inside them. And that sends them into stage 4, which accelerates the protons to 150 billion electron volts, and that injects them into the tevatron, the big 4-mile ring, okay? And it sends protons this way, and it sends antiprotons this way, and what comes, you know, they smash into each other, and it's not pretty, I guess. A question? Yes, sir. Okay, I was told I was the comedian of the club, but I'm not the particle physics expert, okay? That's a very good question. As I was putting this presentation together, I asked myself the same question. I don't know. My guess is that in one of these accelerator processes does it, but I don't know. Sorry. Pardon me? Oh, he's, okay. Where does an antiproton come from? Thank you. Okay. So then they inject them into the tevatron. So here, here is inside the big ring, okay? And all these blue and red things are the magnets in there that are pumping energy into the protons and antiprotons to make them go around. You'll see a little bit more about that later. And then they have these giant experimental machines, the things that detect the results of the collisions. And you can't tell, this thing is probably 25 feet tall. And it's one giant machine after another, after another, after another in their experimental area. And so I got to go in there, and I was very happy to be able to see these machines that I've heard about for so long that does this fantastic work, and see them in person. You know.
Bill, if you don't mind, I'm going to interrupt your,
yes, sir.
to answer the question. This is really fascinating, folks. The creation process follows these steps. First, proton generation. Hydrogen ions are accelerated using the LINAC linear accelerator and booster before being fed into the main injector to reach 120 billion electron volts. The collision. These high-energy protons were directed into a rotating target made of nickel or Inconel. Creation and extraction. The immense energy of the collisions converted kinetic energy into new matter. How you like that?
Okay.
So basically, they are popping into existence,
Yes.
producing a shower of secondary particles that included antiprotons. Magnetic fields were then used to filter out the antiprotons from the other debris. The extracted antiprotons then are stored and cooled, that is condensed into a tight, stable beam in the debuncher and accumulator rings before being shot into the main Tevatron collider.
So you can't go on the street and buy antiprotons.
No,
you got to make them yourself.
Basically, they're made from energy.
Yeah. Wow, that is interesting.
E equals MC squared.
I heard about that. E equals MC squared. And yes, thank you very much. That's a great explanation. Thank you very much. Appreciate it. So here's inside the ring. So the ring, the main ring, accelerates them to 1 trillion electron volts. They be traveling at over 99% of the speed of light. They collide to produce they accelerate them 99% of the speed of light in opposite directions, as we've mentioned, and then they collide to produce quarks and other particles in these amazing detectors. And this is just one of them. There's a whole bunch of them. There's a whole bunch of detectors. Okay, so this is sort of a diagram. Anyway, so over here is that Cockcroft-Walton, that 35-foot tall thing that starts the process. And then here's the linear accelerator. And then here's one of the small injector rings, they call them, okay? And so it injects the stuff into the main ring. And some of them are going this way, and the protons one way, the antiprotons the other way. Then they collide in just the right spot so that the results from that collision, that the particles that are created are sent down this way here to where they have the detectors in their so-called experimental area, okay? I know it's hard to understand all this, but that's basically it. Okay, so here's a diagram of the same thing. Here's the Tevatron, okay? Here's one of the injector rings. The Cockcroft-Walton's over here, the booster ring. It goes around here, gets faster, it injects them into the main ring. Okay, just another way of showing it, okay? That's about all I can say about that. Okay. Okay, so here's a picture from, so here's the big skyscraper. Here's the Tevatron, 4 miles in circumference. Now this booster ring looks like it's about the same size as the Tevatron, but that's just because of the foreshortened view. The booster ring is so much closer. This thing is probably a mile away or something like that. Here's where the buffalo live, okay, where they roam, I guess. The buffalo roam, I guess, I don't. Anyway, and so they go around, they collide over here, somewhere about over here, and then as you can see, these are all the experimental areas off in the distance. So the whole facility is big. Okay, this is a big piece of hardware here. I don't know. And you'll see there's water around over here, and there's water around over here because I know a guy who worked on the magnets. He said they generate a lot of heat, and so they have to have the water for a cooling system, like your car, to cool the magnets down. And I pressed the button. Okay, so then, I walked all through this thing, and it's just one giant detector after another. This is about 15 feet here. I'm only seeing, it's a circular thing. I'm only seeing half of it here. This is the center of the circle. And, what does it do? I don't know how it works. I don't know. And there was nobody there who could have any chance of explaining it to me. But I just wanted to show you, they have many, many detectors, giant machines. I hope not, although that might explain some of my problems. However, 15 years ago, give or take.
These pictures are 15 years ago.
Uh-huh.
These pictures?
Yeah, right. I know a guy who was working there, and he brought a bunch of us from the astronomy club down, and it was. Oh yeah.
Once it was finished, built, and running, that they would allow people in there again.
Well, I know the Fermilab frequently shuts it off. They make changes. They turn it back on. They run for weeks, months, whatever. Oh, they want to make some more changes. They shut it off. So I guess. Okay.
Yeah, they called it CBAF then, Continuous Electron Beam Accelerator Facility, but it's now Jefferson National Lab. But a friend of mine worked there.
Which is where?
Newport News, Virginia.
Virginia.
And anyway, I got to go in the tunnel, but they told me this is a special privilege because once we've been using the thing, we're not going to let the public in here ever again.
You know, I heard about it since I was a teenager. So yeah, it was a definite privilege. I was very happy to make that. So big machines. Press the button. And here's another one. This is a machine that comes in two parts, one side here and the other side there. This part goes into this part here. The thing, look at this is a cage for people to stand in. So this is for a 6-foot person over here. So these are giant things, you know, this is not erector sets, right? This is big, big equipment here, more detectors. And so here I am in the main ring. You can see the magnets here of the various kinds. And you can see the magnets here and over here, and the tubes where the protons go through. And in case you're saying, hey, Bill, you were never inside that ring, I'll say, yes, I know that's what you were thinking, right? That's me over there. Can't you tell by my, I had to wear a hard hat, and there's my t-shirts in the bag. And you can see how the hallway disappears. You're in a big ring, but it's so big, it takes a long time for it to disappear. But that's, I said, hey, I'm in the ring, take my picture, please. So, yes, sir.
Hold it, Mac. Just pass it to Mac.
What's the size of the magnets? How strong are they? I heard nine Tesla at one time, but I don't know.
How strong are the magnets? I do not know. And I don't, to be honest with you, you just mentioned Tesla.
Yeah,
I don't
heard
even know if
9
that's how
Tesla.
they measure them.
Yeah.
So I can't tell you. The guy I knew who worked on the magnets worked on them in the early 70s. So even if I knew, I'd probably be old information. Yes, sir. Oh,
Question, are those superconducting magnets? Are they
the
using super,
the
because
guy
I think
who
it's
worked on
CERN.
them was telling me about superconducting. And I think they might be, but I'll be honest with you, I don't know.
Okay, because I think at CERN, they are
Yeah.
superconducting, but it takes a long time to chill the magnets down.
Yeah. Um, 14 Teslas, not 13. We're talking 14 Teslas here. How much is that? I don't know exactly. It's a lot. It's more than one of the cars, right? More than a Tesla car. If you say so. Okay. Thank you. So here's pictures I took from on top of the skyscraper. What was it, 30 stories high? So you can see the big ring going off in the distance. You can see the water for cooling. You get an idea of the size when you look at the cars, and that's just what it looks like. A lot of grass in between. So then, 2019, they knew that they were not going to be the big Tevatron anymore. CERN was going to take over the proton work. So they did the so-called proton improvement plan, and they were going to update the accelerator complex, started in 2019. And they were going to concentrate on high energy neutrino research, which is what they started, which is what they've been doing since then, okay? To help understand the universe, okay? Because it turns out neutrinos are a real big part of the cosmos, all right? And so they will be the world leader in neutrino research. The name of their project is called DUNE, Deep Underground Neutrino Experiment. I'll explain what all that means. And there's a second part to it called the Long Baseline Neutrino Facility, LBNF. I'll show you what that all means. But that's their big neutrino experiment system. the protons will be accelerated to produce the neutrinos. Oh, by the way, neutrino, it was named the neutrino because the new part of the name means it's neutral. There's no charge to it. And ino means it's really small. So that was a very clever name. It's
massless. They didn't have any mass.
well, people argued about that. And what they say now, and I talked to them recently, they said it's so, if they have a mass, it's so dang small, and I use that language purposely, it's so dang small that you can't measure it. Yeah, now, well, because it's the, yes. Incredibly small. So you don't, there's no published number that tells you how massive it is. There you go, non-zero. Okay. All right. Oh, we'll get to that. Yes. Okay. And they're not finished they are going to have future upgrades to the system to increase the power of their beam. And okay, so that's what they're doing now, neutrino research. Okay, so neutrinos, very small but non-zero. Okay, no electric charge. 3 flavors, the 3 types of neutrinos: the electron, the tau, and the muon neutrino. Okay, and what they told me is we really can't see them. We can only see the results of what they do. Okay, so now we're talking really small particles here. Okay, you can't see them. And this was discovered X years ago. As they travel through space, their flavor, these 3 flavors, changes, and that's what we refer to as oscillation. Okay, and neutrinos are the only particles that do this, so they're really oddballs in that respect. Okay, and this is quantum mechanics. Now I could explain quantum mechanics to you if I knew it.
Which is really bizarre and nobody understands why.
Okay, including me. I don't, okay. So when they learned about the oscillation, that solved the quantum mechanics of it, solved the so-called solar neutrino problem. We saw neutrinos coming out of the sun, and they were the wrong kind of neutrinos. I don't remember what the wrong number of them or the wrong kind. And we didn't understand, how could the sun be producing these kinds of neutrinos? Then they discovered oscillation, and they said, they hit their head like this, and they went, okay, that explains the so-called solar neutrino problem. Question?
The detectors only were designed to detect, I don't know, it could have been like tau or electron neutrinos.
Yes.
So they were missing the other 2.
Okay.
And so they were detecting 1/3, exactly 1/3 of the predicted values.
And that was the wrong number.
It was the wrong number. But it was down by, a nice fraction, like 1/3. And then when they discovered that there were, 3 flavors, it's like, they only had designed to detect 1 type of flavor for them. That's
Right.
why they missed 2/3 of them. So that was pretty cool.
Yeah, that solved
like
that
it solved
problem.
the
Thank
problem.
you. Thank you. So, and then when we started talking about dark matter in the 1990s, people said, I know what dark matter is, it's neutrinos. And then they did a whole bunch of experiments in mathematics and said, no, neutrinos are not dark matter. There are some big sources in the cosmos, some so-called background sources that produce neutrinos, such as the Big Bang and supernova. You may recall in 1987, there was a supernova that we could see actually naked eye, okay, if you're in the southern hemisphere. And so they detected neutrinos coming from the supernova, and they actually used that detection of the neutrinos to pin down precisely where the supernova was. Okay, because if I think I'll mention this, I will mention it, because they go right through anything in a straight line. Their path doesn't get changed by anybody or anything for any reason. Okay. So the Big Bang and supernovas, because they're created by nuclear fusion, all right? They have no electric charge, and they're not affected by the strong force. That's the force that controls the nucleus of the atom. And so they pass through solid matter, planets, bodies, and ghost. So they call the ghost particle. Thousands of, maybe a billion of them go through our body while I'm talking up here, and it doesn't matter because they don't interact with matter. Okay.
Bill, sorry,
Hello.
sorry. Just Steve Clayworth has said on the chat. So some of the neutrinos produced there are aimed toward detectors in South Dakota.
Yes, I will be talking about that.
Oh, is that?
Yeah, I got the whole map here and everything. Thank you. So because they're straight, they're information carriers. They don't get changed by anything out in the cosmos. So when you see the neutrino came from here, you know exactly where it actually came from. Okay. All right. And billions pass through our body every second. They mentioned, and they can pass through a light year of lead. That's nuts to me. That's a lot of lead. A light year, that's way bigger than our solar system. Our solar system is a couple of light hours, and they can pass right through it unimpeded. That's interesting. Interesting particle. Okay. So speaking of South Dakota, so here's the neutrino science. The most powerful neutrino beam in the world, studying the oscillations, the 3 different flavors, the Dune project that I mentioned. So they fire neutrinos underground from Fermilab, okay, to lead, I think it's pronounced lead, not lead, to lead South Dakota 800 miles away to an old gold mine underground, okay? And you know, the Earth, you probably heard about this, the Earth is curved. The surface goes like this. We used to think it wasn't. And so to go all the way 800 miles, they go, well, here's the big, here's Fermilab over here. They create the neutrinos and then they shoot them underground 800 miles. Neutrinos don't mind doing that at all. They go right through anything. A light year of lead, they can certainly make it to South Dakota, right? Yeah. And then they're now currently, as we speak, building all this equipment down over here to detect the neutrinos, to study the oscillations and maybe try to find a mass. Who knows? I don't know. They're trying to learn as much as they possibly can about neutrinos. Now, this, oh, you can see this same chart. So Fermilab, neutrino beam, South Dakota, SURF, Stanford Underground Research Facility. It's an old gold mine, right? And that's what they're building now. Now, here is there's 3 different types of neutrinos. I can't read it. You know, electron, tau, and muon, okay? In 3 different colors, okay? So when we send them, they're virtually all of one type. But we know that after 200 kilometers, many of them will change. After 400 kilometers, more and more and more, until when they get to South Dakota, they've oscillated. They've changed into a different flavor of neutrino. So this is the diagram that shows you basically how they do it. You got the curved Earth here, but the neutrinos go nice and straight, and the gold mine is just in the right place to capture Fermilab's neutrinos. So as I mentioned before, we were able to link up the neutrinos with the supernova in 1987. And so they've set up a system, you know, an internet system, the Supernova Watch. And this is what I was told, okay? 99% of the energy from a core collapse supernova, that's the typical supernova when a star is just massive enough, okay? And the core collapses, it runs out of fuel. 99% of the energy from the supernova is neutrinos and antineutrinos. Now, we know from our astronomy studying supernovas, there's a lot of heat, a lot of X-rays, ultraviolet, a lot of light, an awful lot of energy. And I always thought that's the energy. But it's 99% of it is actually neutrinos. That to me, I found interesting. Okay, and I got this from Fermilab. I'm not going to argue with them.
I don't think it stays neutrinos because there's so many neutrinos,
a lot of
much
them,
mass that it does actually interact. I think I read actually, if you were super close to a supernova, the neutrino flux would be enough to kill you.
You might hurt you right over here.
But a lot of neutrinos, but when there's that many neutrinos, they do interact a little bit, right?
Well,
I think the light year of lead is enough to stop like some neutrinos.
Maybe, yeah.
Anyway, just like the presence of the Earth has been detected by, they can see that there's slightly fewer solar neutrinos arriving in detectors at night and in the daytime.
Yeah, gotcha.
But it takes like years worth of data to see
And
it.
billions and billions and billions of neutrinos. Yeah, right. Yes, sir.
So this is located in the Black Hills,
Say again?
in South Dakota, the Black Hills.
I know it's South Dakota. I don't know if it's officially considered Black Hills. It's a gold mine.
Yes, Native American gold mine, yes.
Okay. So 99% of the energy. So with this supernova watch, the systems are not looking at Fermilab, they're looking out in the cosmos, right? And looking for neutrinos that will arrive. I think it says it here. I did it. I know I did this here. Well, let's see, what does it say? It will be the neutrino detectors will be the first ones to see the supernovas. They will be able to detect the supernova in the first 100 seconds of the event, which is before we would see the light. Okay, light from the supernova can be absorbed and re-emitted before detected. Neutrinos are unaltered. I didn't spell that right. You know what I mean. And so they're accurate messengers in that respect. Okay, the neutrinos arrive on Earth before the light does, so they're an early warning signal. In other words, if the system detects neutrinos, it says, okay, move your telescopes over here. You're going to get some light from a supernova. It's just the way the supernova works. The neutrinos come out first. And also light can be absorbed and re-emitted and stuff like that. No, they don't go faster than the speed of light. That's for sure. But they do arrive here before the light does. And then it gets communicated worldwide over this internet system to tell everybody, here comes a supernova. And they can pinpoint the location exactly, okay? So other projects that Fermilab has participated in, you might have heard of, let's go back to the 90s, the Sloan Digital Sky Survey. They built a lot of the hardware for the Sloan Digital Sky Survey. Here is the dark energy something project, Kit Peak, trying to study dark energy. Fermilab constructed hardware for that. They were very involved in quantum computers. I went to a presentation there on quantum computers 10, 15 years ago, maybe 15 years ago. And they were deep into trying to build a quantum computer. But back then, even today, the quantum computer is this big. It hardly does anything at all. They can just barely get them to work. And back then, they were even smaller. Okay, they were neutrino-sized quantum computers, is my guess. Very small, but they were working on it. And this really struck me as strange, a water treatment system using an electron beam to destroy these so-called forever chemicals in the water. And I said, well, I never would have thought of that. But I also never thought of the fact that they would use the proton beams from the Tevatron to do therapy for cancer patients. And I know a couple of people who participated in that, okay? Because the proton beams can destroy the tumors. Okay, I didn't have that on the list, but I know they did that. So they used to do proton research. Now they do neutrinos. They got these other little side hustles that they do. And yeah, and that's Fermilab. And here they have it. They had a display. If you recall, Sloan Digital Sky Survey, they would look at, they would have a different fiber optic cable for each galaxy that they were going to look at. So all those fiber optic cables had to be mounted on a disc, like on the holes in this disc. So this was an actual picture of the galaxies that they wanted to look at. And so this was used in the Sloan Digital Sky Survey, so-called plug plate. Anyway, so they're involved in many, many other things. And I pushed a button, and that's what I wanted to tell you. Thank you very much for your attention. I have to be in bed by midnight, but I got time for some questions. Thank you. Thank you.
Oh, I have it. And I'm going to ask my question.
Go ahead.
Sorry. Yeah, the question is, has anybody tried to collide neutrinos with antineutrinos? and see maybe a way of detecting what their mass is by the results of the annihilation.
I'm sorry, I didn't get the beginning of your question.
The big,
We know the masses of the proton and,
no, no, colliding neutrinos.
oh,
You can generate, you say, a neutrino beam. You can
Yeah.
also generate an anti-neutrino beam. So why not
Perhaps.
collide the two and see what emerges from the collision?
maybe in their spare time, they could do that. But you know what? Neutrinos,
Yeah.
they can't measure the mass. They have a hard enough time. They can't, and I was told, people in Fermilab say they can't even see them. They can only see the results of their interactions. So that maybe what you're suggesting is still possible, but I haven't heard anybody discuss
Yeah,
that
and
idea.
I have another thought on that. So let's consider a neutrino can go through a light year of lead. If you're sending a beam of neutrinos at a beam of antineutrinos, how many collisions do you think you'll have?
Pretty slim.
Yeah,
Yeah,
yeah. So might not be worth it.
yeah. You know what? Maybe the people at Fermilab have thought about that. Maybe, I'm just guessing.
Thinking neutrinos are chargeless particles. So how do you accelerate a chargeless particle? Accelerate a chargeless particle.
Accelerate them. Right.
That's how you're generating neutrinos going to
South Dakota, yes.
So the question is, maybe you could have two of these things beaming towards each other, one generating antineutrinos and the other generating.
The first thing that comes to my mind is they don't even have this working yet. Okay, they're still building the facilities in South Dakota, so maybe that'll be part two. You know. Okay, any other questions?
We're eight minutes ahead of schedule, so we have time for 8 minutes worth of questions if we want to make.
That's what
them.
happens when I talk fast. Oh, any online questions? Yeah.
I'm just going to read. Steve says the problem is that neutrinos interact so weakly that getting two beams of them to hit each other is like trying to collide two clouds of smoke made of ghosts.
Ghost. Okay,
Okay.
that's kind of what we were thinking, right?
Yeah.
All right, thank you. Thank you.
Who has the next question or comment? Anything from anybody else online? Okay, Lee.
I was going to say, theoretically, how will they know that they are detecting neutrinos from Fermilab in South Dakota with the variability of neutrinos?
I don't know. I don't know. I don't know details at all about what they're building in South Dakota. Okay. The closest thing I've ever seen to detecting a neutrino is the so-called cloud chamber. Okay, where they have a big container of liquid argon. Okay, and the particles like neutrinos and others, when they travel through there, very few of them interact with anything, but they leave a trail as they go through the liquid argon.
Yeah, I think, I mean, the neutrino, like Kamiokande in Japan, the neutrino detector, it's basically like a gigantic vat of some liquid that has the property that the neutrinos are, slightly more reactive with it than normal stuff, because it's got like the right energy level and something. Anyway, and then they see like a little flash, and the photon that's generated keeps traveling in the same direction as the neutrino that hit it.
So
and
as
then they can see what direction the light is going, and then they know, oh, it came from there.
So as the people in Fermilab told me, we never see the neutrino, we just see the results of the
Yeah, and they've
interaction.
done experiments where they sent like a neutrino beam miles. And I remember seeing something where they had like, a circle painted on the wall, and the neutrinos are coming through that circle, and then they had the people walking through it and all, like, it's like, we can walk through the neutrino beam. It's not dangerous.
I'm not walking through there.
But anyway, they actually could get it, a few miles away to like a circle a few feet across, and then they put their equipment there. But yeah,
Did they charge people to be able to walk through that neutrino beam? Because I think that could be very good. That would be great. 50 cents, you walk through the neutrino.
So if you ever see a science fiction movie or read a novel where the main weapon of the battleships is neutrino rays, you'll know that they just don't know their subatomic physics.
I watched science fiction movies at Fermilab. They would, like, once a month they would do and they did a movie called Forbidden Planet. Anybody here know about
Great
Forbidden
movie,
Planet?
great movie.
Okay, saw that show when I was 6 years old. And when they start talking about the technology in Forbidden Planet, all the people, the scientists and technicians at Fermilab were all cracking up laughing because, it was the advanced stuff for 1956, right? Yeah. Okay. Yes, sir.
Hold it, Matt.
So, from my understanding, like the leaders in like particle physics are in like Switzerland and CERN, but weren't they gonna build like an even bigger one in the United States, but it like lost funding or whatever?
I believe the expression is, don't get me started. Yes, in the 80s, we were going to build something called the super colliders. Right. Yes, and we didn't. And it was money and Congress. Probably, I said money, probably politics in Congress, and it was canceled.
Hold it.
So my friend, who's now one of the chief scientists at Jefferson National Labs, he was a PhD student and then a postdoc, and working on the SSC, they called it, superconducting super collider, and they're going to build it in Waxahachie, right very near Duncanville. So actually, all the scientists and stuff that were going to work on it were buying up houses in Duncanville, which is a suburb of Dallas that was closest to where Waxahachie, where they're going to build it. And they started digging the tunnel and everything. So anyway, it's a shame. It's a story that I wish somebody would have documented and written a book, because it was fascinating. Because I was hearing about it from my friend about what was happening, because there was a facility in the Woodlands called TAC, like the Texas Accelerator Center, I think, and they were the ones who successfully lobbied to get it built in North Texas instead of in Fermilab, where it would have actually made more sense because they already had a facility there. But Texas offered cheap land and various inducements. So anyway, and he was giving me a running blow by blow of what was happening with it. And to make things short, basically, he realized this is going to collapse. I'd better take the job at CBAF, Continuous Electron Beam Accelerator Facility, which is now Jefferson National Lab, because SSE, which is like giving me a much better job at a much higher pay and is in Texas where I grew up, it's going to collapse. And the reason was it just completely became about politics. So there were several different teams building magnets, several different teams building like the injectors, several different teams building all the different things that you need to curve the beam and make it the right, density and everything. And every single decision, like, it came down to, where do we need to send the money for this? Not who has the best technical solution. So like they went with like the wrong technical solution for the magnet. They went with the wrong technical solution for the collimator. They went with the wrong technical solution for the injector. Every decision was made by where is the money going to go, not by who has the right technology to make this happen. And finally, when it was really becoming clear that it was just becoming a cluster, they realized they had to fire somebody to make an example, and so they fired the team digging the hole, which was the one team that was on time and under budget.
Okay, we have time for one more question if we have a question. One more question?
Online, any questions?
All right. Bill, thank you so much. This is, as always.
Thank you.
It's great to hear about science with an injection of comedy.
Oh, thank you.
Okay.
Thank you.
All right.